Okay, so next part is, I think the term was cloudification, or agentic control, or remote control. So how do we really do it on the microscopes that we get control? I can take this off and it's maybe better. And we are working on that for quite some time. We are working on this remote control of the microscope with, now I can have a laser pointer, with, it's not as bit fast here, with Remco and Paolo from Thermo Fisher. And we have quite a few people over here on the human intelligence side, right? So we are working on getting our microscope remotely controlled. It's a work in progress, and it took us a real long time to come up with a good framework. If you wonder about why I'm talking about it, I think Sergey alluded already to that. In my master thesis, I already controlled my the microscope at the time remotely. I was acquiring inelastic eel spectra of momentum-resolved eels. That's what we would name it now. At the time, that name wasn't invented yet. We wanted to do energy-filtered diffraction. I called it beer garden automatic because after it finished, it called me in the beer garden, and I had to bike up the hill and switch the microscope off, so it wasn't fully acquired. And I got a lot of flack for my first machine learning papers. People were not very happy about it at that time. So I'm doing it for some time. And the key thing, coming back to Sergey's beginning, we want to be faster, more efficient, and that is clearly where the whole field is moving into, right? And the remote acquisitions also will allow us to completely think differently about how we acquire data and what is possible. So I want to talk about the frameworks that we have. So we have our electron beam on the one side, right? And the detectors. In the center, we have the microscope with all its functionalities. And these functionalities on an electron microscope are almost always from different vendors. So, but if you want to make an interface, you want to make it as universal as possible. Actually, we want to make it so universal that you can run the same framework on PM, or on a 10 stem, on an SEM, on an atom, on a scanning probe microscope, and even on a synthesis robot. Basically, we want to have the whole IAM here, Institute of Advanced Materials and Manufacturing, being able to be remotely controlled. So if you have that kind of restriction, how do you think of a microscope then? Suddenly you have to have a lot of abstraction going on. And so this is where we were about a year ago. So we had the STEM orchestrator. You had to have a lot of software on your computer, on the supercomputer. It worked, It was efficient. It allowed us to do everything we needed, but what it did not allow us was to have a unified interface, whether it's whichever way it is. So, and it was certainly based completely local on some kind or on our specific instrument. So it wouldn't have been easy to transfer anywhere. We had another limitation. We wanted to send many commands in parallel. We wanted to get data back while we are sending commands. So machine learning is sometimes slower, sends a microscope, sometimes vice versa. So this time gap you don't want to wait for, right? Because it just slows you down. The question is, what do we need? And so our framework now is so that the right-hand side, that is you. You in different incarnations, you running a Jupyter notebook on your laptop, on the supercomputer, on a workstation, whatever it is, right? You running a Python script, a user interface. So working with Levi in the moment, making a user interface. And then you also want to have a large language model agent or some amount of machine learning agent that can control it, or any kind of combination. So let's look at our microscope. I mean, just look at it and the complexity, right? Chuk, chuk, chuk. You can put things in and out, and even that is not everything that is there to do. So I can run this microscope, of course, quite fast and easy. You set me in front of a GOL, I have to ask them, where is this button? How do I do that? So I know how to do microscopy, but I cannot work on any microscope. I have been on a neon microscope for a year. I need somebody to help me and remind me, see what's happening, what changed in the interface, and so on and so on. And everybody of you is that way, or maybe you're really geniuses. And if you are so, keep it to yourself, because it must just make us feel bad, right? So anyway, so why is there not a better graphic user interface? Nobody could figure it out, right? So there is just no way to do that. And so I think the way that the field will go, is by using large language models to replace this kind of complicated user interface, or at least help people to navigate through it. And that would be already good, because that would then allow you to use the microscopes to the max with very little learning curve, right? It would flatten the learning curve, and it will free you to have more interesting and more techniques at your available to you. So that's where I want you to think about what we need to be doing. And in order to do that, we have to separate the microscope or any instrument from the user, from the client in the remote in the language of remote microscopy, right? So the client has to be separated, and you have to have a unified interface for that. Where is my button here? Okay. So we wanted to send commands backwards and forwards, and that is called asynchronous. And lucky for us, within the Blue Sky, not the Blue Sky, the social network, but Blue Sky project. So these are the ones that run the synchrotrons. They already have this kind of server software. It's basically a database for servers. So we have the database, and then we have all the different servers behind that. And we have, once we have this database is actually getting you for each server the capabilities. And that will be channeled directly in our MCP server, Model Context Protocol server. So that is what a large language model agent can understand. And so you can directly pull that through. So there's very little that's supposed to be done in such a MCP server. So that was lucky that they were doing that correctly already and getting us all the context for all the commands. The problem is that you have too many commands, so you have to filter it. So the MCP server is actually, for us, a filter of what you can do, which we are not very good right now, but we'll work on that. The data is a different path. It's a so-called tiled server. It's also from the Blue Sky project. So you acquire something, it's going to be on the hard drive, and all you get back through the Tango database is where is that file, and then you can reach that. The nice thing about this tiled data server is it only pulls whatever you need. Everything else, it just leaves there. You can get the metadata, you get the images. If you have a whole stack of images, just gives you whichever one you want. It doesn't slow down the communication. That's the key thing here. So this PyTango goes to a microscope server, which has the different devices on it. And with the microscope, we always develop in sync a digital twin with the same functionality, so that you can test out any kind of code that you have without having to go on the microscope. And when you're on the microscope, you can just try it out. We started doing that with the hackathons. Every December, we have a hackathon. I encourage you to participate. Last year, we had quite a bit of it, so I hope Sergey will talk more about that. I think we do that in the end of that summer school. So we have the real microscope, and that is an abstraction of a TEM stem, right? So all the functionality that a TEM stem has is in the digital twin. How it is implemented is then dependent on the whatever vendors you have around and about. So that is the key. The settings for the microscope are all universal, right? So these ones are servers that are extra. And so think of these things a little bit. And now let's start our server. While I was complaining, Levi and Austin already were fixing our art. So if we go, where is my... it's this, I always have these things in my way. Okay, let's go. Oops, this one here. It started, I know. So I stop it. Nobody can use the microscope now. Okay, remotely. You can go on it, and so it is down. delete, okay, register, okay. So I don't want to do that. I want to wait. Okay. So you start this GUI, and then we were looking at that before. So we clear first all the commands that might still linger there. One of the big problems we had in the hackathons that people had processes running on our port addresses, so you don't want that. First, starting up the Tango database. That is this part here, right? So now I don't even find my mouse. Okay. Still starting. Okay. So it found all the different stuff that is basically just what it now knows what to start up. It runs the camera. You want to operate the camera independently from the stage, from the scan, from whatever. So they have to be in parallel, and they have to be able to get commands and send commands back in parallel. So that's why you need different servers for that. And the Tango database one will allow that. The PyTango, if you look at their web page, so they ran more than 10,000 devices on that without any bottlenecks. So it is a very, very robust thing, and they run it for a long time. So, okay. So now we wait for the corrector. These are Python programs, so they have to be compiled. So they are running. And so this is now where we run the CEO's corrector. So we start this one up. That one takes a while. No, it's ready. Okay. Doesn't say what it's working on right now. I thought it was waiting. Okay. So anyway, all these servers come up, and then it makes a tiled server, so the data server coming up. Huh? I think it got stuck. Not my command. And for each microscope, all you need to do is you just load the different configuration files, right? Here, if you run your less commands, let's say you don't need EDS, then you just unclick that, and then it doesn't start up that server, and you don't have that kind of capabilities. Maybe that's what we should have done. Do less capabilities. Okay. The on-the-fly fix did not really work. Here it comes. Okay. We have a memory allocation server error. That's weird. That's a new one. I think we didn't do something here. Okay, so it was running all the time along, and we'll get it going, but this is what we're doing. That's funny that it works, of course, only not when we are having that in the class here in the summer school. Good. So how should we think about that? Sergey made this nice kind of analogy. You think of the left-hand side here as the brain. This is your nervous system and muscles, and this is your soccer ball that you kick, right? So here we go. We brought soccer into the game here. Change backwards and forward. On the instrument part, you can have any kind of capabilities from yield spectrometer, you could have lasers in there, whatever it is, right? As long as it's a server, it's a device, and that is something the PyTango server will provide to whoever is the client. And this is compatible with the Blue Sky project. So they have this massive orchestration machinery behind it, and the PyTango database then is wrapped by the OFIT interface, and then Blue Sky can do all kinds of orchestration and the most complex workflows. We do not go that route, at least not in the moment. It is quite a learning curve for that kind of machinery. So we'll go and get onto that. So we want to include, for instance, the laser system of the WaveX. So we have a WaveX computer. Switch too often backwards and forward, right? So a laser system, the Gatan computer. We run server software under Gatan. It has a Python interface. So we can acquire yield spectra or whatever Gatan we can do on a Gatan computer. With CEOs, we can do any of the aberration correctors. And then, of course, if we have a different vendor for the holder, for the TM holder, we can do that too. And then you can think about how smart of functions can I have and do I want to have, right? So you want to correct the drift, you want to have automated tuning on while you're acquiring your data. Somebody can watch that. You can do very, I don't know whether any of you ever tried to put a nanoparticle in the right zone axis. It's one of the most aggravating things you can do in a microscope, because you have this small particle and you tilt the sample holder, and you can imagine if you tilt it exactly on the axis, nothing is happening. But if the particle is not on the perfect axis, which it never is, of course, then it moves and defocuses. And so we have a smart tilting one that can do that. I'll show you in a moment. So we want a coherent interface for all clients. It has to be asynchronous. We want to have it smart, so it has to have workflows that are already established and possibly better than what's out there. And that will actually really enable us to be more efficient. So for most parts, the microscope is much faster than a human. Right? So our reaction time is in what, a second or so? But that is without thinking, right? So our thinking is the problem. And if there's an established workflow already, then we can directly do that. We want to have it dynamic, so we want to have it flexible. We want to be having an MCP server, and we want to be compatible with Blue Sky, mostly because they provide very stable server software for that. So that was the different iterations that we went through. We were purely working with AutoScript from Thermo Fisher. Then we integrated things with the PyTango server, and then we went away from channeling the data directly through and went with a tile server, because that lazy transfer of the data really improved our throughput. So we control it by the supercomputer, we saw it on my laptop. We have a workstation, we can see that. And if you want to do lots of different experiments, you want to change your beam current. Our microscope has a monochromator, and we can control our beam current very effectively with the gun lens over the monochromator's entrance. And so if you have a diffraction pattern, you want to be in the order of a few picoamps. And if you do with a 10 picoamp EDS, then you will wait a long time. So you want to have something like 300 picoamp. For EELs, it depends, and it depends on your sample, and you want to change that very quickly. If you watch me changing that, I put the screen in. I have to change the button to the gun lens, right? And then I focus till I am there. That takes a while. By that time, I have possibly destroyed the sample or something else moved away. Who knows, right? Things can happen. It certainly is slow. And if I go between diffraction pattern and EDS spectrum backwards and forwards, we can talk about a minute. So it's not going to happen very often just because I don't want to do it. So you can do one thing is you can calibrate your beam current with and let it run on a Jupyter notebook, and then you just dial these numbers in, and suddenly you can do things very, very quickly. You do EELs with 50 picoamp, you do EDS with 350, and then you go to 5 picoamp to do your your diffraction pattern, and you move backwards and forward. And it does take nanoseconds, of course, right? Because it's a computer. So you want to have that. And it suddenly changes things because now you can do all these different experiments instead of first this, then that. You can do that on the same spot. You can combine them with physical models, right? So here is ballistic damage, and say we're drilling out molybdenum atoms, and we're doing that at random places. And so we're fitting a model on that, and then you can get these kind of things. So if you want to do that controlled precisely by yourself, no, right? So this is something you definitely want to have some kind of remote control. And then the data can be analyzed directly. And then once you know what it's doing, you have a threshold for beam damage. You have or you can just drill holes where you want them exactly. This is the one where we do the tilt. So what you do is you unfocus, you tilt a little bit, you find the area, you focus, you tilt, and that way you never lose the area, and you can tilt 10, 15 degrees in no problem without losing the area. That is one of the things. So you have an interesting area. It looks, of course, differently when it's tilted, and you have to be your own pattern recognition thing. And so this is one way of changing that. So tilt, focus, and bring it back in the same area. That is something a computer cannot do extremely quickly, and that is a workflow, right? So tilt a little bit, bring it back in the same area with either image shift or with the stage, depending on that, and then refocusing, and then you go on tilting till you reach the area. So you can do that on a nanoparticle, and then you, for humans, it takes a little while because you're bored, right, when it's doing that. But it's much more efficient than when you would do that. And of course, you can have your coffee while doing that. So we did the remote aberration correction, right? So we have done that. It just go here. You saw the C1A1 with the OptiSTEM software. We can do that a little bit better. In this case, it was Utkarsh Precious. Can I? Does it run? Where's my? Okay, we want to unlock that. Where's pointer option? No. Just want. There's another easy way.
Hello, so you can see.
But we don't see the sound.
And we are trying to optimize the aberration coefficients. Usually, traditionally, we do it through this software, COS, which is kind of slow. We also use Sherpa to fine-tune the first order and the second order aberrations. For now, let me try to optimize this using my script that I wrote. So this uses Bayesian optimization and Gaussian processes to tune it. And let's see, I ran for C1A1. You would see how here it is adjusting the aberration coefficients and getting images. And once we step into the log, right, let's zoom in. And you would see that there is this data it is collecting, and you have seed points first. And you have other metrics of how well the image that you've taken is doing in terms of those metrics. Well, you also note down the aberration coefficients, and stay tuned. I will show you how at the end what is the image we land with. This is how the PO has started. Sorry, my laptop is a bit untidy. And, it has ran second step, and we are running this for 10 steps. Now the BO is done training. We have around 8 seed points, and I wish I can focus it better. 9 of BO steps, right? And you can see we started with an image something like this, and finally we see these solutions. So if we compare it side by side, yeah. So on the left is the one we started with, and on the right is the one we converged to.
You might or might not remember the OptiSTEM. When I tried to run it the first time, it failed. With the Bayesian optimization that Utkarsh is running. I'm not sure why he runs the Bayesian optimization on his laptop instead of on the supercomputer, but it would be a bit faster then. So let's see what he tried to do. So we have, if we think of machine learning, we'll go into that. We need to know what we want to achieve, which is called a reward function. And in this case, the OptiSTEM is the reward is the highest contrast. And if it is off, then the highest contrast that it will find might not be the optimum contrast. And so in this case, we have 2 different awards. One is the contrast, and the other ones are the bragg spots. no, not pen. So the black spots in the Fourier transform. That is your resolution, your atomic resolution. So if you want to do that as well, then suddenly you have two different rewards or goals. Of course, you want to have the highest contrast with the highest resolution. So it's, however, not trivial to do that with Bayesian optimization, and that is where Sergey comes in. And you can see we go from a rather bad image that OptiSTEM or the other ones would not be able to do, or at least would have a hard time and take a long time. So, so that is where we start. That is the red one. And if we only start with, if we only use no, this is a contrast one, so it was much worse than that. So this is purely the contrast one, the red one. So we optimize the contrast, and that's where we arrived. If we also want to see where the would have a good Fourier transform, then we want to be up here. And we see very nicely, we get, instead of not only the good contrast, but also the nice resolution. In an ideal case, you would want to be on this end here with the highest contrast and the highest resolution. So these are the seed points the Bayesian optimization got, right? So just random parameters, and then it tries to find the new ones. It very quickly went up here and ended up at this point and got the highest resolution and highest contrast. So this is something that doesn't run as fast as we wanted yet, but that's again where I would call on Sergey. So we want to have that. So it will really help everybody to have these kind of things installed. And if that is running on this microscope, it runs on the digital twin. And then if you have that on a GOL microscope with the same interface, it runs there as well, because it has possibly a CS corrector, right? Or any other corrector, because it's independent of that. All we need to change is, and that is something that is actually quite remarkable in that case. There are 7 parameters that have been changed, right? So we have all the first and second orders that are corrected on that one. You try to do that with the OptiSTEM and you're a bit far off. Think of it like 15 minutes, and then you might not get onto that. Another thing that is interesting, you can completely think out of the box and combine things. Let's do 6D STEM. Wasn't there sound with it? I thought we had sound. Anyway, we have these particles. So we take an overview. It's gold particles in TiO2. And it segments it. Segmentation is one of the big problems that is not universally solved, at least not by us. Maybe somebody else has a good idea. Everybody has their favorite one. And then now you have a whole bunch of particles, and you can jump to each of them and get an EDS spectrum. And actually, you don't see that here. It's a bit fast. For each of these particles, the beam is actually taking an EDS spectrum in the middle, and then it runs around the particle to get one yield spectrum for the plasmonic response. So very, very weird things you can do, and you can completely think differently about it. And you get the diffraction pattern for each of them. So you know the orientation as well. So
one question.
One question only. Can you speak in the microphone so that people can hear you? Yeah.
Hello? Yeah, okay. So one question about the segmentation. So if you have a few cluster of the nanoparticle, they overlap together, do you just apply some simple algorithm like a watershed, or you have to do some object detection and do segmentation for that?
Okay, so that's exactly the point. That's where the segmentation comes in. So we can do watershed, we can actually change your workflow and see all the different particles really in your blob, in which case, with the Bayesian optimization, you would take a few pictures and then run. So you can do a lot of things, certainly. It depends completely on your thing. And then you can, so your combination is the key thing, and which combination you want to choose for that is solemnly your problem and of your agent. So the key thing is suddenly everything is a little bit different because we have more capabilities. And the overlapping of particles is a problem, especially if they all have the same size and same shape. So you want to find possibly for your analysis only particles that are round and not larger than that. 29. Maybe that is a requirement for your analysis, and then you can put it in. So this is part of the workflow strategy that you have to develop, and that is where your intellectual oomph will really play a difference. It's not longer on, or hopefully not too much longer on how you align the microscope, or so it's really on the material science side, what is the good sample locations, and then you can find those, right? If you have to find, I don't know, lots of nanoparticles always clump together, they just do that, right? So I want to identify one that is sitting there alone or on the corner. That is something one can find, and one can let it run and let it find, and then it will find them again because it remembers. And then you can think about the next step. Okay, I want to have EDS and diffraction on it, right? But that is exactly where we are going, and we are by far not. We just realized, now we have to think differently about our experiments. And we can focus really much more on the material science. And you can actually now, because it's fast, hopefully to change to different modes, you can have many more methods that are better targeted for what you want to. So, too long of an answer, Minko?
Yeah, thank you.
Sorry. Okay. So we want to make it smarter. We want to make it more efficient. And one of the key things that happens is that you have to have the sample inserted. If you insert a sample, what happens is it will drift because the holder is at a different temperatures and the objective lens environment. And so it takes about half an hour to an hour before it lowers the drift. So the question is, how can you make a lot of experiments without changing the sample holder? Hopefully, during this summer school, we'll get you some ideas of how to do that. Okay, am I happy ahead of my time? Yeah, no, so that's all the different methods that you can use then. And these are 3 different samples drop casted on a microscope grid. And they have different shapes, they have different chemistry. and let the machine learning sort them out. And then we investigate the ones one by one, and we don't have to wait for the sample to be inserted. And possibly, if we have a good workflow in the future, we can have that done automatically overnight. So the workflow then, I can put it here. For random libraries would be, we select the region, make an overview scan, we sort them by, let's say, chemistry. So we have a lot of catalyst samples, so I just got a sample, iridium oxide, iridium with platinum, iridium with niobium. So we have markers for them, right? We have crystalline and amorphous iridium. So we take diffraction patterns as well. So we need the chemistry and the crystallinity of the sample, and then we can sort them out. And then we want to know how is the surface changing. For that, we want to have nanodiffraction on the surface. So we have a workflow that we can do. Other people, we want to maybe have eels on the surface, or, you can do whatever you want to, but certainly you have the possibility to do many different samples, as long as they are having some kind of markers that can be easily differentiated. And I don't know how fast you guys are, but I can do maybe two particles or 3 particles to investigate in an hour. Maybe if I'm really careless, I do 4, right? So we did 110 minutes. Okay, then we have suddenly statistics and not just me as an operator. Okay, so, and then you can use all kinds of different techniques to increase that, to watch that. So lots of different things in here. You'll see this in different contexts probably again. So they collect seed points for BO. That's the same thing for the Bayesian optimization, right? So it's the same thing Utkarsh did with the analysis of the aberrations, just different parameters. Here it's different points. What you have to have is, of course, a very nice interface, right? You have to have the analysis of the data so that you get the relative information out of it. And then once you have that, you can discriminate all the different particles, and it learns what the shapes are and what the differences are. And then if you have a sample that is maybe not uniform, that is also applicable suddenly, because these catalysts are usually not especially uniform, right? So some are more, some are less reduced, some are more or less crystalline. Which one is it that does something? Which one is the most of them? What is optimized for the different samples? So all of these things are now suddenly possible. So it runs through it and it learns which shapes is what, and then after that it can. Takes a while. It's only a few hundred particles that it looks at, right? So what can you expect? And in the end, it kind of classifies which particle is what. Let's see whether we have some overlapping one, the images, and whether it finds them, because there are some. Where is the end of it? Okay. You getting there? So you see it switches on and off the beam, so we have minimal beam damage while doing that. In this case, we did not switch the... Okay. I thought the end of it. Wow. The end of it was usually a classification, and you can see there was this bigger square ones, the round ones overlapping on one of these ones. So, and it will actually recognize the two different ones. So you can do with the microscope recrystallization. So this is an atomic resolution image. That was our first attempt. Wow. So we, the way that works is the electron comes in and gets backscattered. If it's backscattering, the impulse has to go somewhere, and that's the atom. And if that is hard enough, it moves it a little bit. If that is close to the interface, it comes predominantly in a rest where the crystalline structure is. In the meantime, we figured out why I couldn't get all the way to the top. And we did that by having this kind of technique automized. So you see the dimensions are in the sub-nanometer range. What you don't know is that the top part is actually where they have implanted arsenic as a delta function. So this is actually an arsenic-doped nanoparticle. And what you can do is you can drill holes, and so you can separate it out. So you have an arsenic-doped nanoparticle with exact dimensions. Of course, the reason I did it was to have a power T. Notice the stacking faults. So that is something that happens when there is arsenic implanted. And then you can make different parts and different holes. What we're doing right now is we are playing around with the different parameters, see how far we can, how fast we crystallize. And so then we have all the parameter to do that more effectively and more precise. So that's one of the things we are doing. And now is a good time for having Levi coming up. We can. How do I control the That's very easy. While you set up, I explain how I control the orientation. So I need a basis for the recrystallization. So I need a seed, right? A nucleus. And that is my substrate, right? So that is silicon itself. And so the only place silicon wants to go predominantly is at a silicon space. Or, as we saw, if it can't get there because there is too heavy of an atom in the way, the next best one, which is a stacking fault. So it's just really depends on your on where you crystallize on. If you try to do that in the middle of nowhere, in the amorphous region, you're not going to get any kind of amorphization. Oh, I have to allow. We have several mice here. I have to get out of your way here. Which one is which one? No, this is that one. Okay. Too many mice. I get out of your way, man. Good. You're on? Yeah. Is it not? Okay. Hold on. Stop sharing. So now we are unshared. And you? Do you not share? Share. Where is your share button? Screen.
Wow.
Okay.
So this is one of
Oh, hold on 1 second. So this is Levi Dunn, working with me for 1 year now. He is a high school student. Microphone. He has to get a microphone, and I have to get rid of it. Get him. And yeah, he just won the first prize in material science in the International Science Fair, and also the local one, of course. It's what made him. That's what paid him to go to the international one. So we're very lucky to have him now as an undergraduate student. So
this is our agentic platform. So I'm going to share a short video, which is our first ever acquisition of an image. Yeah. So yeah, this is, okay, can everyone see this? So this is the first time we acquired an LLM actually acquired an image on the physical microscope. And so, yeah, we're going to start the LLM through a Jupyter notebook. Currently now we use Python scripts, and we have a GUI that we can start. We start the MCP server through GUI. We can start all the other servers for the actual microscope through that GUI. And then we also have a GUI where you can kind of work with an LLM. And so you can, maybe if you have the LLM acquire EDS, you can perform like an elemental analysis of that image. And so the cool thing about LLMs is I'm not actually a microscopist. And so the only thing I can pretty much do is maybe acquire an image or something. I can't even move the stage or something. But with an LLM, I can do a variety of things, require EDS, perform pretty complex experiments. So we've had to start an LLM at a position, and it can navigate back to that position. And yeah, you can do so many cool different things with that. And the cool thing is the LLM actually can write its own code. And then let's say it failed. And so in this video, it actually failed, and it rewrote the code and then managed to acquire an image. And so it's kind of cool. It just reiterates and perform multiple execution steps. Let me show an image. Okay. So this is an image of the kind of the agentic framework. So you have your user, you have your GUI, your API, and your command line interface. Then you have your data abstraction layer. And so that makes your scientific data something that the agent can understand. So you might have like a HDF5 or something file. Agents can only understand like a PNG or something. And so that kind of converts that file format into something the agent can understand. The MCP, that's where you can build an MCP for pretty much anything. So you might have an MCP for an SPM. So that's what Boris is working on. And we have our MCP for the STEM. And so the agent can actually connect to multiple of those and control various different devices. And here, okay, so here are some of the GUIs. So you haven't seen this GUI, but this is for our MCP. And then we have our server startup, and this is what we were running on the actual microscope. And then this is Goose, which is basically a way to connect to MCPs. It looks a lot like ChatGPT. We use a local model, but you can also use like API keys. So you might have your ChatGPT subscription, or your Claude or your Gemini subscription, and you can talk with the agent and perform experiments through this. So currently it's not working. We actually have so many functions that the agent doesn't really understand what to do. When we started out, we had very few, but we've focused so much on building the framework right now, and expanding that to various other instruments. But this is basically asking to list all the available functions. So you can see there's quite a few functions. This is all for the STEM. Yeah, and that's about it.
Well, thank you. Get my microphone back. Excellent. We had some questions, how we do EVS and diffraction on the same part. Okay, good. So we have to take the camera in and out. So we take a few diffraction patterns and then take the camera out, and then we take the EDS the yield spectra, because all of them need the zero beam. So very good observation. So lots of things have to happen there, and of course a human knows that, and a large language model would have to figure that out. We don't want that. So if we say acquire an yield spectrum, first thing is take the camera out, the main screen up, take everything out of the way, take an yield spectrum. So it's requirements. If you want to have a large language model to do that, it can, but you're out of your tokens in no time. And $20 will not be sufficient to do that. So you're talking more like $1,000. So what you want to do is you want to minimize also the large language models by providing only relevant commands that you want, that you need. So, and then you can actually do that. Where do we want to go with that? We'll find out in the long run here, hopefully. We would want to go where different agents from different instruments work on the same material, not necessarily at different times, but hopefully at the same time. So something is looking at samples, and then it comes up with something to synthesize a little bit differently. So that's the idea behind it. And is there anything else in the chat that we have to talk about? Okay, so that was a little bit of a... First, we had an introduction to electron microscopy and also the vocabulary that goes with it, right? So that we know what we are talking about. And so that was now an overview of where we want to go and what the framework is. And now we get into the details of the machine learning, and Elizabeth is gonna tell us about neural networks. The hackathon that we do today will be on using a small neural network to do atom finding. Okay.